Multi-backbone continuum robots, such as the ones shown in these two videos, are constructed using super elastic backbones that can be used to bend the device to achieve various shapes, as can be seen in these videos. Those are called backbones, and by pushing and pulling on them, they can be bent in various shapes. These devices have a variety of advantages, including macro motion capabilities and large workspace. However, there's a variety of applications that require different kind of capabilities. Even though these devices can provide deep access into the anatomy and they're suitable for surgical applications, as these examples show here, they generally cannot provide motion at the micro scale. However, there are a host of applications that could benefit from an accuracy of below 100 micron. We're talking about preferably applications that require on the order of few microns or even sub-micron precision. Those applications include image-based biopsy and in vivo monitoring of tissue. For example, OCT can provide micrometric scale image resolution, but intracavitary OCT for 3D image-based biopsy requires micrometric motion accuracy and microscale motion. Image-based diagnosis and surgery at a cellular level has a huge potential, provided that we can achieve motion resolutions of at a cellular level. Similarly, microvascular reconstruction, nerve repair, and grafting require these levels of precision. And there are a host of industrial applications such as in-situ OCT inspection. For example, microfluidic devices could be inspected using imaging modalities in situ. The predominant solution in the technical community has been historically the use of a macro manipulator, as can be seen here, and a micro manipulator, as can be seen here. This is called serial stacking of macro and micro manipulators. However, this approach does not scale down well for surgical applications. So the problem that we're looking at, can we have a dexterous continuum robot with both micro and macro motion capabilities? And the solution that we came up with is the idea of continuum robots with equilibrium modulation capabilities, or in short, CREM. The idea is basically very simple. By using the traditional actuation of these tubular backbones using push-pull actuation, we can achieve the macro scale large workspace. And by changing the stiffness distribution along the length of these devices, for example, by sliding micromotion wires here, we can actually adjust the equilibrium shape of these devices by minute amounts and achieve micromotion capabilities of these devices. This is an example of such a device that we constructed in our lab. It's a continuum robot here with several backbones and with an integrated OCT probe. And what this video shows here, initially, it will show the motion of this optical marker that's being tracked under a microscope. Over here you will see the micron scale motion that is generated by the robot as the micromotion wires are inserted through the backbones. And you can see the trace here. You can see also the motion at micron scale. And we have created both a control approach and a theoretical model for these devices that were initially presented in these two papers. Then we subsequently ventured to explore the feasibility of 3D OCT of these devices using both external and internal OCT probes. In this example, we're showing the experimental setup with an external OCT probe and a microscopic camera for tracking the motion or observing the motion of the device. And we are looking at the feasibility of achieving 3D optical coherence tomography volumes using these micromotion control of these devices while holding the sample in front of the external OCT probe. For example, we are scanning the threads of a miniature screw. What you can see here, each one of those lines represents what we call a B-mode image of the OCT probe, and the stacking of these images is achieved by micromotion modulation of the equilibrium shape of the device. Each one of those imaging planes is separated by almost 1 micron. Similarly, cellophane tape can be scanned, and 3D volumes of these scans can be generated, and similarly a channel in agar can be scanned, and this is the volume that's generated. And we can see that using our approach for control and imaging, we can actually achieve fairly high accuracy in estimating measurements from 3D reconstruction, and we compare them to typical 2D images of these samples. And these are the reported accuracies of the reconstruction. And as a sample application, we looked at the feasibility of scanning the retinal nerve in a swine eye. This is an example here, and what you can see is the branching of the optic nerve. As you can see, these are 2 B-mode images. And on this side here, you can see the 3D reconstruction in one view showing the branching. And so you can see right now the 2 branches, and then later you will see it spin and show basically the one side where it exits with 1 branch. Later, we looked at the feasibility of the idea with a miniature probe that can be attached to the robot or inserted through the robot. This is the probe shown here, this is the actuator, and this is the integrated system. And as what you can see here, this is us imaging an agar channel, and these are the 3D reconstruction of the channel and also a 2D view of the channel. Next, we demonstrate the feasibility of OCT-guided visual servoing. You will see this needle being driven into a channel within an agar medium. Both macromotion and micromotion are being used using redundancy resolution with OCT feedback. As a first step, we label the agar channel, and then we label the tip of the needle or the edge of the needle as viewed in the OCT. And initially you will start seeing the needle move laterally, then in the depth direction. Now you can notice the needle almost starting to move, and you can notice it now moving here in the OCT view laterally, and you can also see it here. Then you'll start seeing it advance in the depth direction once it is above the agar channel. Finally, we'd like to acknowledge the funding by the National Science Foundation.